most amazing feats of intelligence known today are performed by networks of neurons. In both brains and artificial neural networks, there are millions upon millions of these neurons connected to each other. And while together they can perform amazing things, individually they're quite simple in comparison. You can even think of them as this fundamental unit of computation, like a transistor. So each neuron receives inputs from other neurons that come before it. If these inputs exceed a certain threshold, the neuron becomes active, and then it sends its outputs to the neurons that come after it. For many decades, neuroscientists on one hand, and engineers and physicists on the other hand, benefited from an interaction between the two when trying to understand neurons and neural circuits. So neuroscientists were able to understand the electrical properties of neurons by viewing them as electrical devices, just like a radio or microphone. And engineers, on the other hand, were inspired by how biological neurons connected to each other and then coded up artificial ones in their simulations in the same way. And this ushered in a new paradigm of computation, which is the neural network. Now, to go from these simple neural networks to these complex, incredible devices that we have today required the work of many researchers and many years of work. So I'm excited to tell you a little bit about some of that today. I'm Louis, and I lead a computational neuroscience research group here at RIKEN Center for Brain Science in Japan. The Nobel Prize in Physics 2024 was awarded to John Hopfield and Geoffrey Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks. So the press release goes in a little bit further. John Hopfield invented a network that uses a method for saving and recreating patterns. So for biological neural networks, these would be memories. When the Hopfield network is fed a distorted or incomplete image, it methodically works through the nodes and updates their values, so the network's energy falls. Okay. Geoff Hinton used the Hopfield network as the foundation for a new network that uses a different method, the Boltzmann machine. This can learn to recognize characteristic elements in a given type of data, and as we will see, be able to generate new data based off of these elements. So these concepts might feel a bit mysterious to you, but hopefully by the end of this talk, you'll be able to understand at least a little bit of what they mean. So let's start with the Hopfield network. Like any other neural network, the Hopfield network is composed of neurons, and when it receives an input, some of these neurons become activated. Now, this input for biological systems like the brain are experiences or events in our daily life that we want to store as memories. For artificial neural networks like those used in AI, these inputs are data that are used for training. So in this talk, I'll use all three terms kind of interchangeably. Okay, so how do you know which neurons are active when a neural network receives an input? Well, this is based on a rule. In biological neural networks, this rule is governed by the complex interactions of neural pathways in the brain. And so this rule is not fully known. And actually, a big goal of neuroscience is to figure out what this rule is. Now, in artificial neural networks, this rule is just dictated by the engineer. The engineer codes up what this rule should be. So on one hand, for example, for this image, it can be a pixel rule so that each neuron corresponds to one pixel in the image. If the pixel is dark, then the neuron is active. If the pixel is light, then the neuron remains inactive. Alternatively, this is a more abstract rule. There's a list of concepts, and if a concept is present in the image, then the neuron becomes active. If the concept is absent, then the neuron remains inactive. So either way, this pattern of activity, which neurons are active in the network, encodes or represents this image or piece of data. So in a sense, it acts kind of as a barcode for this piece of data. Okay, so the Hopfield network stipulates that whenever two neurons are simultaneously active, there's a connection that forms between them. And so in this image, when it's fed to the network, you see that these are the connections that are active. When a second image is input into the network, other neurons become active and connections also build between them. When you take away the input, then there are no inputs that are active. And so the pattern, the network is silent. But still, there are the connections that are stored in the network. Those persist. And so actually in the Hopfield network, these connections are what store memories from previous experience. And so in the same thing will happen for biological networks as well. In our brains, it is thought that these connections are what stores memories. Okay, so this is how these memories are stored. Now, what about retrieval? Suppose your friend asks you, Louis, you had this wonderful trip to Mount Fuji. Was there anything interesting you remember seeing? And you think, yes, saw this beautiful mountain with a lake in front of it. And there was something interesting in the water. Was it a bird? So as you try to remember what happened at Mount Fuji, your brain is activating an incomplete set of neurons in one of these patterns, maybe primed by this question. And through the connections that were previously formed, these active neurons will activate other ones inside the same stored pattern, and this will complete the memory. Now note that in this example, the 3 neurons on the right only receive one connection from an active neuron, so this is not enough to activate them. Okay, so that's how the Hopfield network stores and retrieves memories. But what Hopfield offered goes beyond just these rules. He offered a new abstract way, a physics way of thinking about this memory network. In the Hopfield network, just like in any other neural network, different patterns of activity or states are possible. And you can imagine arranging these different patterns of activity along an energy landscape, such that patterns that are more similar to each other are located closer in this landscape. What Hopfield found was that the process of receiving an input, activating certain neurons, and building connections between them is mathematically equivalent to carving a well, a memory well, centered around the active pattern. And so that when there's a second input, it also carves a second well, and so on. So now these features in the landscape are what store the memories. What about retrieval? Well, you can imagine that when you initiate your network with this incomplete memory, it's placed on the landscape as a ball centered around this incomplete pattern. And the process of retrieval, Hopfield showed, was mathematically equivalent to letting this ball roll under the action of gravity. And thus, it will roll to the bottom of the completed memory well, and you'll recall the memory. Okay, so this process sounds a little bit arbitrary and a little bit unnecessary. We could perfectly understand the network through the connections. Why do we need this complicated landscape? Well, it turns out that often in physics, through abstraction, you can reveal the full power of a network or a system. So this process of abstraction, such as the field in quantum mechanics or the metric in general relativity, led to developments, outstanding developments in these other areas of physics. And the same happened here. So you can ask, well, can you create more diverse and rich landscapes? And moreover, can the action of the network not just fall under gravity, but can the network explore all these rich features of the network? So these features are made possible by the Boltzmann machine. The Boltzmann machine extends beyond the Hopfield network in 3 key ways. First, there are additional neurons that aren't activated by the same input rule like the original neurons are, but they are instead activated through their connections with the other neurons. So this reflects a common theme in machine learning that simply with more neurons, you can increase the computational complexity of your network. And now, unlike the Hopfield network, the number of neurons isn't limited by the number of pixels in your image or the number of concepts in your concept list. The second key development is that each memory, each input, only carves a small shallow well, such that now the landscape that is formed by your network doesn't reflect individual memories, but it instead reflects the common features across all of these memories, or the statistical distribution of them. And now the third key development is that Hinton gave the network a bit of an internal energy, like a little vibration. In physics, this is akin to a temperature. So with this internal energy, the network is now free to explore these features of the landscape and not just fall under the action of gravity. And it might end up in a state that didn't correspond to any that it saw before. And this might correspond to a new data, a new image that it has never seen before. But instead, the network generated this piece of data based off of all the other images that it has experienced. So this is an early example of generative AI. So now when we go back to the citation, I hope you can appreciate how Hopfield's network can save and recreate patterns. And in the brain, this is equivalent to storing and retrieving memories. When the Hopfield network is fed a distorted or incomplete image, it works through nodes and updates their values so the network's energy falls along the energy landscape. Now, Geoff Hinton used this network to develop the Boltzmann machine, and it can recognize characteristic elements in a given type of data. And as we see, it can generate new pieces of data based off of it. Now, like any other research, this work didn't occur in the vacuum. It was inspired by work by other researchers. Interestingly, in the Wikipedia article for the Hopfield network, it originally had some other researchers named in the first sentence, and this has since been simplified. I will just highlight the work of one of these researchers, Shun-ichi Amari, who's a colleague here at RIKEN Center for Brain Science. Amari's network is very similar to the Hopfield network and was developed about 10 years earlier. It contains the same rule for building connections between neurons. It can also the same rule for activating individual neurons. And it also shares the same inspiration from neuroscience, citing here the work and theories by Donald Hebb. Now, I will say that Hopfield's energy and memory landscape interpretation of the network really helped to popularize it. And let's leave history aside now and fast forward to the present. And in present day, we have these incredible neural networks that can do amazing things. And this is made possible indirectly by the work of Hopfield and Hinton. But recently, researchers have been appreciating that there might be a more direct connection. For example, the transformer architecture in OpenAI's GPTs are very similar to Hopfield networks, as well as the diffusion models in Stability AI's Stable Diffusion. So the work of Hopfield and Hinton is still very much relevant in modern AI. And it is also relevant in modern neuroscience. So Hopfield networks are being used to understand human memory. And many groups are working on this, but I will just share you some of my own research performed in collaboration with Taro Toyozumi, who's also a colleague here at RIKEN Center for Brain Science. Memories in the brain are stored by an area called the hippocampus. And in particular, there's a region in the hippocampus called CA3 that has these connections between neurons that are thought to act as a Hopfield network. Now, the memories, the inputs from CA3, come from entorhinal cortex. And this entorhinal cortex sends these inputs along two different pathways. First, there's this direct connection through the orange perforant path. But before reaching CA3, this path branches off to the purple mossy fibers. The question is, why are there these two input pathways into CA3? To study this, we model this area of the brain with a series of neural networks. So the CA3 region is modeled as a Hopfield network, and the memories that we want to store, the experiences, are these images, these fashion MNIST images, each of which is an example of a concept, either sneakers, trousers, or coats. What we have found is that these two pathways, the orange and the purple, carve different types of wells into their memory landscapes. The purple pathway carves wells that are a little bit narrower than the orange one. And moreover, when more memories are stored, similar memories are located closer together in the orange pathway compared to the purple pathway. And the net result of this is that as we store more and more memories, the purple pathway can maintain distinctions between all of them, whereas the orange pathway has these wells that merge such that you no longer recall the individual memories, but instead some kind of concepts that are learned across these individual memories. So here, these sneaker and trouser images are very similar to the average sneaker and trouser images formed by just averaging the inputs. And you can imagine that there are different tasks in life where you would prefer to use one version of the memory versus another. If you want to recall something very specific, like what did I eat on this day, then maybe the purple path is more useful. But if you were to want to recall general properties or fit in new pieces of data, such as seeing a new insect and wondering if it's a butterfly or a moth, then maybe the orange pathway is best for that. And in my research group, we are also thinking about applying these memory landscape concepts to disease as well, in particular to seizures. So imagine that there are these two types of energy memory landscapes. And now imagine that we are giving the system a shock, something that might induce a seizure. And this will correspond to a lot of internal energy in the network. Well, with the memory landscape on the left, there are these barriers between different states, and this might naturally constrain this extra activity. Whereas on the right-hand side, in this landscape, there are these paths around the network that do not have barriers. And so this might help amplify this excessive activity into a seizure. So our prediction is the right kind of memory, the one on the right side, is more susceptible to developing seizures than the landscape on the left. So I hope these few examples have given you a feeling for how these concepts by Hinton and Hopfield are carving a bright future for not only AI and neuroscience, but perhaps even medicine. And I would like to thank all of my group members and colleagues here at RIKEN Center for Brain Science who have made my work possible through this very supportive network. So now I'll just go over 3 questions that I've been asked about this. The first question is, I'm curious about how AI hallucinations relate to biological mechanisms and their risks in AI systems. I'm concerned that generative AI often provides false information. So it is true that this generative process of these networks can be very powerful, and it's a dual-edged sword. So on one hand, it can create new data that is tailored exactly to what you're asking for, even if it hasn't seen this request before. But on the other hand, this new data could actually incorporate different previous experiences in a way that is false and misleading. So it is just, I can only say that it is a big topic in AI to try to steer or direct these systems towards producing truthful yet flexible responses. The second question is, what is the relationship between memory landscapes and language? Language, like many other cognitive functions or types of data, do rely on memory. So I would say that there is an underlying landscape that language takes advantage of. However, language, as we know, it's sequential and it's dynamic. It doesn't just stay in one state. And so this kind of memory landscape might be tailored to not just store individual experiences, but maybe sequences of them. And certainly it is still a big outstanding question in neuroscience to figure this out, as well as a big question for the machine learning community onto how to optimize these networks for language. So the third question is, given the rapid development and performance improvements of generative AI and large language models, is it simply the size of the network that drives this performance? Well, I would say that it has been repeatedly shown that larger networks are simply more capable of performing sophisticated computations. So as the physicist Paul Anderson once said, more is different. But there are two other key factors. One is the size of the data set. So with larger collections of data, there are more nuances in the data that the network can learn to make their responses more lifelike. And the third feature is the complexity and the structure in the neural network itself. So there are certain neural network architectures that have been developed that are especially suited for different types of data. And sometimes this architecture is even inspired by neural networks in the brain. So for example, the convolutional neural network used to process images is very much influenced by how the visual system in the brain processes incoming visual data. So I hope you enjoyed this talk. And if you have any other questions, feel free to leave them in the comments below, either in English or in Japanese, and I will try to get to them and answer them as best as I can.